Thank you. Well, I'd like to thank the organisers very much for giving me this chance to speak. What I have to say could really have been done at almost any point in the last 120 years. It is 120 years exactly since Frobenius's 1897 paper starting our whole wonderful subject. It would have been slightly prescient to have done it more than 50 years ago because you would have had to invent simplex homology, but you can phrase all the results without that. But that was part of the motivation for what I want to tell you about. So let me start with some background. So fix throughout this talk, please, a natural number n. Let f be a field of characteristic p, let's say, and let m be the natural permutation module with a basis e1 up to en permuted by Sn. So I'll define the boundary maps from simplicial homology. So I'll define delta k from the kth exterior power of m going down 1 degree to wedge k minus 1 m by given a k wedge product ei1 wedge up to eik. Its image under delta k, and I'm sorry, I'm writing my maps on the right, which I know is now hopelessly old-fashioned, but, well, you'll just have to put up with it, I'm afraid, is minus 1 to the j minus 1, because I like to start positively, times ei1 wedge, and then you delete the jth term. So that is a hat, not a wedge, which means that you delete it. Okay, so, well, then it's a simple exercise to check. I'm sure we've all done it at least once, that if you take delta k plus 1 and then do delta k, so I'm composing from left to right, which is the way I read English, is 0. So the image of delta k plus 1 is contained in the kernel of delta k. And in fact, the image is equal to the kernel. And there's a very simple way to see it, which is algebraically relevant to what I'll do. So let me show you. So given some u in the kernel of delta k, there's this little calculation, a sort of form of suspension. I'll come back to that. So you take e1 wedge u, which is now gone up 1 degree. So it's something to which I can apply delta k plus 1. And when you do this, you'll get E1 by a kind of Leibniz rule. You'll get E1 delta 1 wedge u if I choose to delete here. And if I choose to delete over here, well, there's a minus sign because I'm starting one position later. And I get E1 wedge u delta. But we don't really have to worry about the sign very much because, of course, u is in the kernel of delta k. So this becomes 0. E1 delta 1 is the, you could think of it as the 1 in the field spanning the 0th wedge power. So this is simply u. So this shows that the image and the kernel coincide. And the short sequence wedge k plus 1 m to wedge k m to wedge k minus 1 m is always exact. So let me make that point 1. And when it's natural to ask when it's actually split, so when can I write the middle term as the direct sum of an image and kernel? And one can show that we have wedge Km is isomorphic to the kernel of delta K, and then the image as a complement, something isomorphic to the image of delta K, if and only if P does not divide N. But in general, it's not split. And, well, you can see example there for P is 2. Just to give a very simple one, this would be the kernel of delta 1, which is the same as the image of delta 2, so it's not splitting off. Well, let me just sketch the proof of this. So if P does not divide N, then M has a direct sum decomposition, I'm sure we all know, as the Specht module Sn minus 1, 1, and a copy of the trivial module. So by standard exterior power identity, this is equal to the kth wedge power there. And then you would take the trivial once, so getting the k minus 1th exterior power there. And you can identify this with the kernel of delta k, and this with the isomorphic to the image of delta k. And these are also certain Specht modules, but I don't need to go into that. So in particular, the full sequence wedge n m to wedge n minus 1 m and so on, wedge squared m to m to the field is exact and split exact, by which I mean that we have the property in 2 if and only if P divides N. Now when P does not divide N, thank you. So when P is more than 2, everything I've said holds for P is 2 so far, although it has a slightly different character because, of course, the signs are irrelevant. But everything I've said is true, unless it's also wrong for odd prime because I've made a mistake. No, I believe everything I've said is true for P is 2. But when P is greater than 2, the situation is quite simple, almost literally, because these modules are simple. And when P divides N, you still have fairly good control. So each wedge Km has at most 4 composition factors, which can be described very explicitly. And in particular, the homomorphism space between any wedge Km and, say, wedge K minus Tm is always 0. Well, it's 0 if and only if, to be very precise, T is at least 2. So you can't get any interesting maps by going down more than 2 degrees. But when P is 2, things are completely different. And I'd like to tell you the story of what the mod 2 homology looks like when you allow yourself to go down by multiple degrees. So section 2, mod 2. So we'll take P as 2. And then we can identify wedge Km with a permutation module, F omega K, where omega K is all those K subsets of 1 up to N. And what is the analogue of the boundary maps? Well, it now makes sense to consider them going down more degrees, because we will get something that is non-zero. So I'll define for t a natural number a map xi upper t lower k from f omega k down to f omega k minus t by, and now we see another suspension principle, but you should be able to guess what the definition is. So y psi t k, so if y is a k subset, this should be the sum over all z subset of y, such that the size of z is the size of y minus t z. And if we taken t to be 1, then this is the analogue of the boundary map, because I'm simply going through deleting exactly one element, with the signs now being irrelevant. So we have for x in omega k plus t, x xi t k plus t xi t k. So I've now got to go down to certain z like that. So there'll be certain z subset of x. I've gone down by 2 steps. So the size is now minus 2t z with some coefficient. And I can predict the coefficient by drawing a little diagram like this. So I can get to z by going down to any y where I remove t elements from x. And in total, I've got to remove 2t elements. So it's a choice of which t of the 2t elements that go down from k plus t to k minus t that I remove. So the number of choices for y is 2t, choose t. But as you can see from my Pascal's triangle on the right there, mod 2, this is 0. So again, we have that the image is contained in the kernel, which means we can define homology groups, and it's very natural to ask when these are non-zero. By the way, it's great fun. It's a bit like the Gauss schoolmaster exercise. Get your students to compute Pascal's triangle mod 2. They will do it by patiently adding up an enormous Pascal's triangle using the full storage space of their brains to get numbers like 252, 210, and so on. And then they will eventually produce something that looks almost but not entirely like that. And then you can point out that they haven't understood the first principle of modular arithmetic. Anyway, so here is a theorem. With parts analogous to 1, which I rubbed off but was claiming exactness, and 2 over there. So the sequence f omega k plus t, f omega k to f omega k minus t is exact, and I spent some of yesterday patiently dotting my T's and crossing my I's. No, sorry, it's the other way around. Well, something like that. And I can characterize exactly when this thing is exact. So, but really, it's the if direction that is most interesting. So, if and only if T is a 2 power, and either, well, if t is 1, then we have the familiar situation, so it's certainly exact then. Or this condition that 2k plus t should be less than n, or 2k minus t should be more than n. So there's going to be a range of n in the middle where it fails to be exact. But if n is large compared to k, or if k is very large compared to n, while still fitting into my setup, then it will be exact. And when is it split exact? Well, if and only if it's exact, so we've got that condition. And then you see this number again, 2k plus t should be congruent to n modulo 2t. So in particular, if you take the smallest n for which this says it can be exact, then it is in fact split exact. But it's really quite rare for it to be split exact. And this gives you some rough idea how the proof works. It's inductive, showing that it is split exact in the smallest case, and then by a fairly intricate calculation, winching oneself up. So let me just make a couple of quick remarks on this. So some idempotents that are relevant to this splitting in two. So idempotents relevant to two were constructed by Steve Doty, Karen Erdmann, and Anna Henke in 2007. But I'm not using their results explicitly, but I think one could probably use that as an alternative route to some of these results. And well, let me just say a tiny bit about necessity. So if you're not a 2-power, then there's a really big obstacle to being exact, which I'll show you here. So if we have t is 2 to the tau plus t primed, with t primed less than 2 to the tau, so I've taken off the biggest 2-power that I can find in t, then you can factorize the psi map, the phi map, or have I been writing psi? I have been writing psi. Psi t factorizes as 2 to the tau psi t primed, which follows from a picture a little bit like this, replacing this with 2 to the tau plus t primed and 2 to the tau, which, because this addition is carry-free, means the binomial coefficient is non-zero. I do recommend the combinatorics of binary carries to you. It's an astonishingly rich subject. It even includes group cohomology as a special case. Well, arguably. And we have, so by this factorization, the kernel, well, it will certainly contain the kernel of psi 2 to the tau, because that's one of the factors. I'm omitting all the degrees here, by the way. You'll just have to work out what they should be, or omit them yourself. So it will certainly contain this, which will contain the images, because we always have some kind of chain complex. And this will certainly contain the intersection of the images, which again, from the factorization, because we can factor psi t through either of these maps, this contains the image of psi t. So if you're going to be exact, all of these have to be equalities. And unfortunately, it's not completely obvious that they're not, but you can show that at least one of them will fail whenever the condition doesn't hold there. So this is used to show one is necessary. And if n is not in the range there, so if n is less than 2 to the k plus t and n is greater than 2 to the k minus t, well then there is a very simple reason why it can't be exact. There is a composition factor of f omega k not present in f omega k plus t or f omega k minus t. So again, that's a fairly blatant obstruction to exactness. And we can see it here. So say we're doing the two-step homology, which is where I started with this whole game. And let's do it with the odd degrees. So I'll start in degree 5, and we have the psi map going over here. Well, its image will be this bit here. It's an injective map. So this is the image of phi from degree 5 in degree 2. The kernel is this part, and the quotient, therefore, so the homology in degree 3 is therefore isomorphic to d42, d42, which is an example of one of these basic spin modules. So as a byproduct of this, one gets really, I think, quite an elegant construction of these spin modules for the symmetric grouping characteristic 2 that gives one an explicit generator modulo the image for them. Okay, so let me just finish then for perhaps 2 more minutes with some ideas for further directions for this. And it started off just as a fun little project about all I could do given my teaching load. But now I'm starting to find it actually, it does have some hidden depths. And perhaps some hidden shallows as well. So let me just propose a couple of further directions that I might look at. And if you find it interesting, you're very welcome to talk to me. I would welcome a collaborator on this. So we started with any characteristic, and then we went to characteristic 2 with these f omegas. So what if we now go back to arbitrary characteristic? So there are some signs you can get some rather intriguing homology, but you can't do it just by having the same kind of map at every point, because this key property of binomial coefficients was very specific. So this 2t choose t always being even. It's very special to the even case. So you need to mix up the boundary maps a bit. So for example, let me do it just by an example. Say I go up by 2 steps, and then up by 1 step. So then I've got 3 choose 1 is the relevant thing, which is congruent to 0 mod 3. So that's degree 3, sorry. So then I step by 2, step by 1, and so on. This is a chain complex. And you can show that the homology is non-zero in at most 1 degree. Where if it is anything, where it's the sign module. So one way to interpret all of this is in terms of categorifying certain binomial identities. So let me just give some examples. So the delta exactness categorifies sigma minus 1 to the k n choose k is 0. This is just a thing where you take the dimensions in a chain complex and pick up the homology groups. And the Xi2 almost exactness, if you work out what the theorem's saying, then you'll see that it fails in at most 1 degree. That categorifies the sum over all j minus 1 to the j. Well, let me just give you the even case, 2m, choose 2j. This turns out to be minus 1 to the m over 2, 2 to the m, if m is even, and 0 otherwise. So let me just squeeze in here. So if you would like to perhaps categorify the identity 7 choose 0, 7 choose 2, 7 choose 3, 7 choose 5, 7 choose 6, I think you'll find that this is minus 1 follows from, well, okay, it follows from adding them up, but I would claim a more elegant proof is to say it categorifies a certain construction of the sign module, although maybe that's complete overkill. One final plan is to extend all this to Hecke algebras. I think there should be some interesting Q binomial identities to be found there. And of course, you can apply the inverse Schur-functor and get something related to the Koszul complex. But we're often seeing cases where the inverse Schur-functor fails to be exact. So again, I think there will be some further interesting homology to be seen there. Okay, thank you very much. David.
Two things. How did you work out that H3 was non-split? And do you see any other interesting modules popping up in the model?
Yeah, good question. So the reason H3 is non-split follows from this is that as I said, I can give you an explicit generator for this. And using this explicit generator, I can write down an endomorphism theta such that theta is non-zero and theta squared is 0. In fact, the square of theta, the image of theta, is contained in is contained here would be in S42 modulo the image intersection. So by the time you've applied theta, you've got quite a familiar object. So that's why the extension must be non-split. So what was the second part?
Other homology models that arise, do they have spec filtration? Young modules pop up?
Right. Yeah. So in the split case, we're getting an explicit construction of certain Young modules. But in general, so if you look at this example, then you're seeing some really rather strange and intricate modules. And I'm not sure in general they will have Specht filtrations. One sign that something quite curious is happening is if you just take, say, the kernel of delta. So it's very tempting to say that this is the kernel of delta. So delta can be thought of as psi1. But that can't be quite right, because then you'd have the image would be split, and it just doesn't fit there. So what's actually happening is that you have some kind of diagonal sitting inside there. And just for even this to be possible, for this quotient to be right, you have to have some interesting ext. You have to destroy any ext that would remove the possibility of an f which got in the way of this extension there. So these modules have some quite curious.
Drawing those modules with line diagrams instead of just the radical series, they look very bizarre. Right?
Yes, exactly. You know what I'm getting at then. Yeah, so they're great fun to play around with.
More questions? If not, we use the sex as a mark for